Whenever we've been determining the potential of a cell so far, we've always had standard conditions. And standard conditions are defined that your gases are at 1 atmosphere of pressure and your solution concentration is at 1 molar. But what happens if you don't have standard conditions? Well, if you don't have standard conditions, then we have to use the Nernst equation to determine the cell potential. And this, again, since you've already done your reading, you see that this equation, you've already seen this one. This is what we were determining before, and that little 0 up there means standard conditions. But now we're saying, okay, well, what if they're not standard conditions? Now we're going to be determining the standard potential of this, or the potential of the cell at non-standard conditions. I've already, again, as you've read, the N is the number of electrons that are transferred, and then Q is the reaction quotient. It's going to look a lot like equilibrium quotients that we've seen before, but we're not at equilibrium, so we're going to call it a reaction quotient instead. So let's walk through example 9.6, and I'll show you how to plug all these different pieces in. He gives you just basically the standard notation for the cell and says use that to determine the cell potential. Well, in order to do that, in order to use this equation, there are several things I have to know. First, I have to know what the standard potential of the cell would be. So it means I'm going to have to know what the half reactions are so that I can use the table in the back of the book. I'm going to have to know what the balanced equation for the overall reaction is so I know how many electrons are transferred. And then I'm also going to have to know the full equation so that I can figure out what the reaction quotient is so I can plug in the appropriate concentrations. So let's take that step-by-step format. So we know that the left-hand side of this is going to be the anode. I'm not going to draw this out, but the reason I'm reminding myself of this is so that I know, okay, which side am I gaining electrons, on which side am I losing electrons? Well, the anode is oxidation, the cathode is reduction. So what that tells me is that I have cadmium and a cadmium ion. And so if I'm going to have an oxidation reaction, that means it has to look like this, because this is an oxidation reaction. I have lost electrons on this side. On this side, I only have lead ions and lead. And so again, it's a relatively simple one to put together here, because if the charge is going to be reduced, then I'm going to have to go from Pb2 plus. I'm going to add 2 electrons to that to get Pb. And as it's supposed to, in one reaction, I've gained electrons, and the other side, I've lost electrons. Okay. Now, if we look at the table in the back of the book, you will see that the standard potentials for these are, this one is 0.403 volts. And then this one is -126 volts. Those are standard potentials. And so therefore, if I add those two together, then the standard potential for the cell is 0.403, and I'm going to subtract that 0.126, and that's going to give me 0.277 volts. Okay, we've done enough of those. I'm going to assume that you know how to do those by now. Okay. All right. Then the overall reaction. Luckily, in this one, I've lost 2 electrons and I gained 2 electrons, so they are already balanced out, so I don't have to multiply anything. If they were not the same number of electrons on both sides, I would have to multiply one of the equations or both of the equations by something so that I had the same number of electrons on both sides. We've done examples like that before. We don't have to do that here, but if you do a problem like this and the number of electrons gained and lost isn't the same, then you'll have to multiply that through in order to get it so that you have the same number of electrons. Okay, so I'm going to write the overall formula, or the overall on that equation. So that's going to be cadmium plus a lead 2 ion yields a cadmium ion plus lead. And again, atoms are balanced and I have a positive 2 charge on the left and a positive 2 charge on the right. So I can see that it's balanced just by doing that. Okay. Now, if you recall, when we write reaction quotients, I am going to use the concentrations. I don't put in solids. Okay, so we knew that this was aqueous, this was solid, and this was solid. So therefore, the reaction quotient is going to be the concentration of the cadmium over the concentration of the lead. Again, remember that if there were coefficients in front of the cadmium or the lead, they would have to go up here as a coefficient or as an exponent, but I don't have that here. If there was a 2 in front of there, then I'd have to square this. If there was a 3 in front of that, I'd have to cube that. But because they're just ones, I don't have to worry about that for this one. But watch out for that in case you have a problem where you do have to do that. Okay, now I have all the information that I need, and so I can use the Nernst equation. So the E of the cell equals the standard reduction potential for the cell, which I already calculated was here, was 0.277 volts, minus 0.05916 over N is electrons transferred. So here it's 2. If I would have had to multiply through, then you're going to use whatever number you got once you've got everything all balanced out, the final number of electrons that were transferred. Okay, times the log of the reaction quotient. So the cadmium, they told us in the notation for the cell was 2 molar. So I've got 2.00 up here, and then the lead, it told me was 0.0010 down here, okay? So now it just becomes a plug it into your calculator and chug it out. I would start over here, divide that out, take the log of it, multiply by 0.05916, divide it by 2. Once you have that number, make it negative and add it to the 0.277 volts. And you should come up with an E for the cell of 0.179 volts. So if you don't get that answer, you probably plugged something in wrong. So I would go back through and make sure that you have plugged everything in correctly into your calculator. You're using your log correctly and all that kind of fun stuff. Okay, so that is using the Nernst equation if you have non-standard conditions. If you have standard conditions, 1 molar, 1 atmosphere, you don't have to go through all this. It's only if you have non-standard conditions.